Physics 6607, Practice 2 Review, Special Relativity, Multiple Choice Question Solutions. We will have a summary of the key concepts and equations for special relativity, and then practice questions, multiple choice questions that are solved. Special Relativity Summary. Let's start with inertial reference frames. An inertial reference frame does not accelerate. It is either at rest or moving with a constant velocity. Every body in the frame remains at rest relative to the frame unless acted upon by an unbalanced force. Newton's laws are valid within an inertial reference frame. We then have the Galilean Newtonian relativity principle. The basic laws of physics are the same in all inertial reference frames. If you're inside an inertial reference frame, you don't know if it is at rest or moving at a constant velocity. If you did, then that would violate the Galilean Newtonian principle of relativity, as the laws of physics would not be the same. An example is if you're in a car and it's got a very good suspension, it's a big car, and you're on a very smooth road, if you're going a constant 40 miles an hour, and again, you can't hear anything outside the car, or if you're sitting there on the road, you can't tell the difference. However, the Galilean Newtonian transformation equations for position and velocity between inertial reference systems did not work for objects moving near the speed of light, or for electromagnetic waves, which move at the speed of light. Two other questions were troubling scientists in the 19th century. Waves require a medium to travel in. For example, water waves travel in water, sound waves travel in air. What medium does light travel through? It does not have a medium we can see, like water or air. Does the speed of light change depending on which reference frame it is measured in? It was believed that light moved through a substance called the ether that permeated all of space, since waves needed a medium to move through. And we have solar radiation coming from the sun. It's got to go through something, so they postulated it was ether. Michelson and Morley then thought that the speed of light would be different as the Earth moved through different points in its orbit, since it would be moving either against or with the ether, or perpendicular to the ether, or other angles. The experiment was set up to measure a difference in the optical interference pattern resulting from the assumed different speeds of light due to the Earth's position. They considered the experiment a failure, as no difference was discovered. However, it was not really a failure. It helped eliminate the theorized presence of the ether. Even though they personally considered it a failure, it really wasn't. Einstein's theory of special relativity, which applied Hendrik Lorentz's mathematical transformations between moving reference frames, explained that the speed of light is not affected by the direction of the Earth's motion. Einstein created two major postulates for the special theory of relativity. What are postulates? They're statements that are made without a solid proof, but have been experimentally shown over and over and over again to be how things really work. So the first one, the laws of physics have the same form in all inertial reference frames. Very much like Galilean Newtonian relativity, but it was expanded to include electromagnetism, which is light. Light propagates through a vacuum with speed c, the speed of light, roughly 3 times 10 to the 8th meters per second, as long as it is measured in an inertial reference frame, and it is independent of the motion of the light source or the observer. It's the same everywhere, no matter how you measure it, as long as you are in an inertial reference frame. What if you are not in an inertial reference frame? That means your reference frame is accelerating. That does allow for different speeds of light in a vacuum, but that's general relativity, also by Albert Einstein, and is not covered here. Simultaneity. In relativity, an event, in bold here, is defined as occurring at a specific place and a specific time. We call that space-time. If two events happen at the same place in space, then it is easy to determine if they are occurring at the same time. Special theory of relativity explains that time is not absolute. Observers do not necessarily agree on time intervals between events that happen at different places in space-time, or whether they actually occur at the same time or simultaneous. Special relativity has had a huge impact on our knowledge of the universe. And again, you have to be moving near the speed of light for these effects to come into play. So we have time dilation, length contraction, relativistic linear momentum, relativistic kinetic energy, total energy, and then the relativistic addition of velocities. We will now go over those consequences one by one. Time dilation. That is the time interval between two events measured by an observer who sees the events occurring at the same physical place, and that is called proper time, or delta t0. An observer moving in a different inertial reference frame, where the events are occurring in a different physical place, measures time, delta t, as the proper time divided by the square root of 1 minus v squared over c squared, where v is the relative velocity between the two different inertial reference frames. Proper time is always the smallest time interval measured by anybody. The factor multiplying proper time occurs so often in relativity that it is given its own symbol, gamma, and is called the Lorentz factor. So gamma is 1 over the square root of 1 minus v squared divided by c squared, where v is the relative velocity between the two inertial systems. Then you can write delta t is equal to gamma times proper time interval. Time dilation effects are not noticed until gamma is very large, where the relative velocity between the systems is very big. Length contraction. It's the formula here. Let's define proper length, which is L0. That is the length of an object measured by an observer in a frame at rest relative to that object. The length of an object in an inertial reference frame moving with respect to the object is proper length. So if you're in a spaceship and you're measuring the length of your table, that is the proper length. Someone outside your spaceship moving in a different inertial reference frame will be measuring L. And length contraction means things get shorter from the view of that other inertial reference system, and it only occurs in the direction of the object's motion. L0, proper length, is always the largest measurement of an object's length. Relativistic linear momentum. Experiments have actually demonstrated that linear momentum changes at relativistic speeds as shown here, where it's regular momentum, well, obviously it speeds moving, not obviously, but it speeds moving way less than the speed of light, times gamma. Mass is considered invariant. It is independent of its speed and must have the same value in all reference frames. Older textbooks talk about a relativistic mass, which is equal to gamma m0, where m0 is the rest mass, the mass of the object at rest. Momentum, the product of mv, is not invariant, but m is. And again, you will find other textbooks that show something different. Relativistic kinetic energy. At relativistic speeds, the formula for kinetic energy is modified and has once again been experimentally proven, most notably in high-energy particle accelerators. And here's our equation for relativistic kinetic energy. It's equal to mc squared over square root of 1 minus v squared over c squared minus mc squared, which is gamma minus 1 times mc squared. The term mc squared is velocity independent. It is also called the rest energy, E sub r of the particle. This is Einstein's famous equation, and it shows that mass is just another type of energy. Let's talk about total energy now. We have our kinetic energy formula here, and then it works into gamma mc squared is going to equal kinetic energy plus the rest energy, and we write it that way, Ke plus E sub r. We're going to let this gamma mc squared term be total energy, and total energy will equal gamma times mc squared. And then in words, there's a lot here, so I recommend going back to the notebook presentation on this. Total energy of something, of a particle, is equal to its kinetic energy plus its rest energy. And the rest energy is when it's not moving. By combining the relations for energy and momentum, we get the following expression. Total energy squared is equal to p squared c squared, that's momentum squared c squared, plus m squared c to the fourth. Now what if you have particles that have no mass, like photons? You lose this term, and you're just left with total energy is momentum times c. So even photons that don't have any mass have a momentum, and the momentum is equal to their total energy divided by the speed of light. Relativistic addition of velocities. A lot of words on this page, but let's go through them. A spaceship traveling very fast, and we leave that vague as there's no hard and fast rule as to when you need to consider relativistic effects. Depends on how accurate you want your results. Okay, it emits a light beam in the forward direction. So we have a spaceship and it emits light in that direction. So this is light. Classical physics would tell you that the light beam's speed would be greater than the speed of light as measured by an observer in an inertial frame at rest relative to the spaceship. So if I have somebody over here and they're watching this, they think that light is going to be the sum of the speed of light plus the speed of this spaceship that's going very, very fast. However, that doesn't happen. Light always travels in a vacuum at a constant speed in any inertial reference frame. Nothing can exceed the speed of light. So this person down here observes the light going at the speed of light, 3 times 10 to the 8th meters per second, and so does a person on the spaceship. He also measured, he or she also measures it at 3 times 8 times 3 times 8, 10 to the 8th meters per second. So there is a new formula to find the speed of objects when they're moving at relativistic speeds, when you have to add them together. So in this case, you have a spaceship going 0.6 c relative to Earth, where we have a stationary observer. We're assuming the Earth isn't moving. And then it shoots a rocket at 0.6 c, an exploratory rocket. The speed of that rocket is not 0.6 plus 0.6 c. You'd get 1.2 c. You can't have that. However, you have this formula to find its speed, where you have the v of the spaceship, the u of the rocket, and then the denominator, it's 1 plus vu divided by c squared. And that will give you an answer less than the speed of light.